Welcome to Quantum Theory, a journey through the strange and beautiful world of physics. This is your gentle guide through the mysteries of the quantum world, a space where particles shimmer between possibilities, where time and reality bend, and where curiosity becomes calm. So go ahead, dim the lights, settle in, and let your mind drift. Whether you're here to learn, to relax, or to fall asleep under the stars of science, you're in the right place. And if you enjoy this journey, please remember to like and subscribe so you can return anytime and explore even deeper. Now, close your eyes if you like, breathe softly, and let's begin our journey into the quantum universe. Imagine standing on a quiet hill at night, gazing up at the stars. Each one is a distant sun, bound in vast orbits, following the elegant choreography of the cosmos. For centuries, we believed we understood that dance. Thanks to the work of Isaac Newton in the 17th century, we had a set of rules, laws of motion, of gravity, that could predict the movement of everything from cannonballs to comets. This was the age of classical physics. It painted a picture of a well-ordered universe, almost like a grand machine. Everything had a place, a purpose, and most importantly, everything could be calculated, at least in principle. If you knew the starting point and all the forces involved, you could predict what would happen next, and then after that, and so on into the future. It was a comforting idea. The universe, it seemed, was rational, logical, and ultimately understandable. But as the 19th century gave way to the 20th, cracks began to appear in this beautiful machine. Scientists started to investigate the tiniest parts of nature, atoms, electrons, and light. And there, at the smallest scales, the universe no longer behaved as expected. It didn't follow Newton's rules. It didn't obey the tidy equations that worked so well for planets and pendulums. Instead, it got weird. Take light, for example. For a long time, physicists thought of light as a wave, much like ripples on a pond. This idea explained many things, like how light bends when it passes through water, or how it can spread out and interfere with itself. But certain experiments didn't add up. One of them was the photoelectric effect. When light shines on a metal surface, it can knock electrons free, but only if the light has a high enough frequency. Brighter light didn't help if the frequency was too low. According to classical wave theory, this made no sense. Why wouldn't more light, even if it's lower energy, eventually knock electrons loose? Enter Albert Einstein, who proposed something shocking in 1905. What if light wasn't just a wave? What if it also came in little packets, discrete individual chunks of energy? He called these packets quanta of light, or photons. It was a revolutionary idea, and it earned him the Nobel Prize. Suddenly, light wasn't just a wave, it was also a particle. This strange dual identity, of light behaving as both a wave and a particle, became one of the defining mysteries of quantum theory. But it didn't stop there. Matter, it turned out, could do the same thing. In 1924, a young French physicist named Louis de Broglie proposed that if light could act like a particle, maybe particles like electrons could act like waves. It sounded absurd, but experiments later confirmed he was right. Electrons, tiny specks of matter, could create interference patterns, just like ripples of water when passed through a narrow slit. Matter had a wave nature too. Suddenly, the line between what was solid and what was not had begun to blur. But the most profound challenge to classical physics came from a man named Max Planck. In 1900, while studying how objects emit heat and light, for example, why a heated iron rod glows red and then white, he encountered a mathematical disaster. The equations of classical physics predicted that an object should radiate infinite energy at high frequencies. This was clearly impossible, the so-called ultraviolet catastrophe. To solve the problem, Planck made a bold move. He assumed that energy could only be emitted or absorbed in fixed amounts, tiny, indivisible chunks. He introduced a constant, now known as Planck's constant, to describe the size of these energy packets. It was a patch, a trick to make the equations work, but it worked better than anyone expected. Planck had unknowingly opened the door to an entirely new understanding of nature. This idea, that the universe operates in discrete, indivisible steps at the smallest scales, lies at the heart of quantum theory. It's a theory built on probability, not certainty, on potential, not predictability. In the world of classical physics, if you knew everything about a system, every position, every speed, you could predict its future exactly. In the quantum world, the best you can do is calculate probabilities. Where might the particle be? What might happen next? There's no way to know for sure until it actually happens. That alone would be strange enough. But as scientists dug deeper, they discovered even more bizarre phenomena, particles that can be in multiple states at once, that influence each other instantly across space, that only seem to decide their behavior when we observe them. Quantum theory was more than just a new branch of physics. It was a philosophical earthquake. It challenged our ideas about cause and effect, about time and space, even about the nature of reality itself. And yet, despite its strangeness, quantum theory works. It predicts the behavior of atoms with astonishing accuracy. It explains why the sun shines, why atoms don't collapse, and how modern electronics, from computers to smartphones, are even possible. Still, this success came at a cost, the loss of our classical certainty. We traded the clockwork universe for one of mystery and chance. In this audiobook, we'll travel deeper into this strange land, from the puzzling nature of particles to the dizzying idea of multiple realities. We'll look at the math, the experiments, and the theories that define quantum physics. And we'll ask the big questions. What is reality? Do we shape the universe by observing it? And is there an end to the weirdness? But for now, remember this: the world you see, the world of solid things and certain outcomes, is only part of the story. Beneath it lies a deeper, stranger world, one where the rules are different, and the truth is not always what it seems. Welcome to quantum theory. Let's start with a question you've probably never had to answer. What is light, really? You might say it's something that helps us see. Sunlight, lamplight, the glow from your phone screen. That's true. But when we ask what light is in a deeper sense, what it's made of, how it behaves, things get much more interesting and a little strange. For a long time, scientists thought light was made of waves. In the 19th century, experiments by Thomas Young and others showed that when you shine light through two narrow slits, it creates a pattern of bright and dark bands on a screen. This is called an interference pattern, and it's exactly what you'd expect if light behaved like ripples on a pond. When two waves meet, they either reinforce each other or cancel out. That's what created the pattern. Case closed. Right, light is a wave. But hold on. In 1905, Albert Einstein explained something called the photoelectric effect, a phenomenon where shining light on certain materials causes them to emit electrons. Here's the catch. It didn't matter how bright the light was. What mattered was its color, or more precisely, its frequency. Low-frequency light, like red, wouldn't knock out any electrons, no matter how intense it was. But high-frequency light, like violet or ultraviolet, would even at low intensity. This didn't make sense if light was just a wave. According to classical theory, a brighter wave should deliver more energy and eventually knock electrons loose. But that wasn't happening. Einstein proposed something radical. What if light wasn't just a wave? What if it also came in little packets of energy, each one carrying just enough punch to dislodge an electron? These packets would later be called photons. Suddenly, light had a dual identity. In some experiments, it acted like a wave. In others, it acted like a particle. Both descriptions were true, depending on how you looked at it. This was one of the first signs of the wave-particle duality, a core idea in quantum physics. But the story doesn't end with light. A few years later, in the 1920s, a young physicist named Louis de Broglie turned the idea on its head. If light, something we thought of as a wave, could act like a particle, could the reverse also be true? Could matter, like electrons, which we always thought of as particles, have wave-like properties? It sounded far-fetched, but de Broglie backed it up with mathematics. He proposed that every particle of matter has a wavelength, depending on its momentum, its mass and velocity. The smaller and faster the particle, the shorter its wavelength. At first, this idea seemed more like philosophy than physics. But in 1927, an experiment at Bell Labs confirmed it. Electrons, fired through a double-slit apparatus, just like the earlier light experiment, created an interference pattern. The electrons were acting like waves. Let that sink in. Individual particles, tiny bits of matter, could interfere with themselves, just like light. They weren't just little balls bouncing around. They had a kind of wave nature, a probability wave, that described all the places they could be until we looked and found out where they actually were. This is the moment quantum theory stepped beyond light and into the matter itself. It meant that at the most fundamental level, the universe wasn't made of solid, tiny spheres like Newton imagined. Instead, it was made of entities that blurred the line between particle and wave. Things didn't have precise positions or velocities until we measured them. Until then, they existed in a fuzzy cloud of possibility. The implications were staggering. If even electrons had wave properties, then so did atoms, so did molecules. In fact, in theory, everything does. Even you. You too have a wavelength. But it's so small, due to your large mass, that it's undetectable in practice. Still, quantum physics suggests that all matter, from photons to people, exists in a strange in-between state where the classical categories of particle and wave just don't apply anymore. Here's the key idea: the nature of something depends on how you observe it. Ask light if it's a wave, and it will show you interference patterns. Ask if it's a particle, and it will come at you in tiny measurable packets. Ask an electron where it is, and it will give you a range of probabilities, not a single location, until you go looking. This flexibility, this duality, isn't a flaw in the theory, it's reality at its most fundamental, and it challenges the assumptions we've had for centuries, that things have definite properties, whether we observe them or not, and that the universe just is in a fixed way, independent of how we look at it. What we're seeing here is the breakdown of everyday logic in the face of quantum logic, and this is only the beginning. In the next chapter, we'll explore a principle that strikes at the heart of predictability in science, the uncertainty principle, a discovery that tells us not just what we can't know, but what nature itself refuses to allow us to know. We're heading deeper now, into a world where certainty is replaced by probability, where measurement changes reality, and where the very act of asking a question affects the answer you get. Welcome to quantum mechanics, where light is a particle, matter is a wave, and reality is far stranger than we ever imagined. We've now entered a world where light can act like a particle, and matter, like electrons, can behave like waves. A world where the very act of observation can change what's being observed. But if that sounds strange, just wait. Because now we come to one of the most famous and most misunderstood ideas in all of physics, Heisenberg's uncertainty principle. It starts with a simple question: can we ever truly know everything about a particle, like where it is, how fast it's going, and what direction it's heading? In classical physics, the answer was a confident yes. If you know an object's position and momentum, which is just its mass times its velocity, you can predict exactly where it will go. That's how we send rockets to Mars, or catch a baseball. The world, it seemed, was predictable if you had enough information. But in 1927, a young German physicist named Werner Heisenberg showed that in the quantum world, this certainty completely breaks down. His principle stated that there's a fundamental limit to what we can know. The more precisely we try to measure a particle's position, the less precisely we can know its momentum, and vice versa. Let's be clear, this isn't a flaw in our technology. It's not just that our microscopes aren't good enough. It's a built-in feature of reality. Nature itself refuses to let us pin down both position and momentum with absolute precision at the same time. The more tightly you squeeze down on one piece of information, the more the other slips through your fingers. To understand this better, imagine trying to locate an electron. Because it's so small, you can't see it directly, so you shine a beam of light to detect it. But photons, the particles of light, have energy. When they hit the electron, they disturb it. Use low-energy light, and you don't get a sharp image. Use high-energy light, and you knock the electron off course. Either way, your measurement changes the thing you're measuring. This is the essence of quantum uncertainty. It's not just about how well we can observe, it's that the act of observing changes what's there. It's like trying to measure the height of a wave in a pond by dropping a rock into it. The rock creates new ripples and alters the wave itself. Heisenberg's discovery had huge implications. It meant the universe is not like a giant clock, ticking along predictably. It meant that the fundamental building blocks of nature are not little billiard balls bouncing around with fixed trajectories. Instead, particles behave more like probability clouds, fuzzy patterns of where they might be, or how fast they might be going. This new understanding reshaped science. physicists realized they couldn't talk about certainty anymore. Instead, they had to talk about likelihoods. Where is the electron likely to be? What's the probability of finding it in a certain place, with a certain momentum? These weren't philosophical guesses, they were hard math, with incredibly accurate predictions, but they were still probabilities. The uncertainty principle also shattered another assumption that we, the observers, can stand outside the system and simply watch. In the quantum world, the observer is part of the system. By looking, we affect what we see. This raised deep questions about the nature of reality. Does the electron have a position before we measure it, or does our measurement somehow create that position? Is the universe a set of hidden variables, operating behind the scenes, or is randomness baked into the fabric of reality? Einstein, for one, was deeply uncomfortable with this idea. He famously said, "God does not play dice with the universe." He believed that there had to be something deeper, a set of hidden variables that would restore order and predictability. But so far, all the evidence points in the other direction. Nature, it seems, does play dice. Now you might wonder, does this uncertainty only affect things at the atomic level? The short answer is yes. In your everyday life, quantum uncertainty averages out. We don't notice it when we drive a car or throw a ball. That's because the particles involved are so numerous, and the effects so tiny, they cancel each other out. But at the atomic scale, uncertainty rules. In fact, if uncertainty didn't exist, atoms wouldn't exist either. Think about the electrons orbiting a nucleus. If they had exact positions and momenta, they'd spiral into the nucleus and disappear. But uncertainty creates a kind of quantum pressure that keeps them at a stable distance. It's not just a weird rule, it's the rule that makes stable matter possible. So the uncertainty principle is more than just a scientific idea. It's a statement about the limits of knowledge and the nature of the universe itself. It tells us that reality isn't something fixed and solid beneath the surface. It's something shifting, something probabilistic, something that won't give up its secrets without a trade-off. You can know one thing or the other, but never both. Not exactly. In the next chapter, we'll explore what this uncertainty leads to. One of the most famous and bizarre experiments in science, Schrödinger's cat. We'll meet the idea of the wave function, learn what it means for a particle to be in multiple states at once, and dive deeper into the mystery of quantum superposition. Because if uncertainty shook the foundations of science, superposition flipped the table entirely. Imagine a cat. It's sitting inside a sealed box. You can't see it, you can't see it, you can't hear it. All you know is that there's a strange quantum device inside. Something involving a tiny bit of radioactive material, a Geiger counter, a vial of poison, and a trigger mechanism. The rules are simple. If the atom decays, the Geiger counter detects it, the poison is released, and the cat dies. If the atom does not decay, nothing happens, and the cat lives. Now here's the quantum twist. According to quantum physics, before we look inside the box, the atom is in a superposition, both decayed and not decayed. And since the fate of the cat is tied to the atom, that means the cat is also in a superposition. It is both alive and dead at the same time. This is Schrödinger's cat, a thought experiment dreamed up in 1935 by Austrian physicist Erwin Schrödinger, not to explain quantum theory, but to challenge it. He was disturbed by the idea of superposition, the notion that quantum systems exist in multiple states simultaneously until observed. So he created the cat paradox to show just how bizarre, even absurd, quantum logic becomes when scaled up to everyday objects. But here's the thing, as weird as it sounds, superposition is real, and it's one of the key features of the quantum world. Let's break it down. In classical physics, something either is or isn't, a switch is on or off. A coin lands heads or tails, there's no in between. But in quantum mechanics, particles, like electrons or photons, can exist in a combination of possible states until they are measured. This mixture of all the possible outcomes is called a wave function. The wave function is a mathematical expression that describes everything a quantum system could be. It doesn't say the electron is here. It says the electron has a 30% chance of being here, a 50% chance of being there, and so on. It's a probability cloud, not a definite location, but a spread of possibilities. And here's the strange part, those possibilities are real. The particle isn't undecided, like a hidden coin under a cup. It genuinely exists in all those states at once. It's not until we look, until we observe or measure, that the wave function collapses and the system chooses a definite outcome. This is superposition. An electron can spin both clockwise and counterclockwise simultaneously. A photon can take multiple paths through an interferometer at once. And yes, in principle, a cat can be both alive and dead, until we open the box. The question is, what causes the wave function to collapse? What makes the electron decide to be here or there? No one knows for sure. Some physicists argue that observation causes the collapse. The act of measuring forces the universe to pick a state. Others suggest it's not human observation, but interaction with the environment that causes collapse, a process called decoherence. As soon as a quantum system becomes entangled with the outside world, its delicate state of superposition breaks down. Then there are the boldest interpretations, like the many worlds theory. It says that the wave function never really collapses. Instead, all possible outcomes actually occur, each in its own parallel universe. In one universe, the cat is dead. In another, it's alive. Both realities exist, side by side. You just happen to be in one of them. Wild, right? But even without diving into parallel worlds, superposition is a verified, measurable phenomenon. It's not just theory, it's been seen in countless experiments. Particles do interfere with themselves. They do exist in multiple states, and scientists have even created small systems, made of many atoms, that behave like Schrödinger's cat, existing in superposed states for fractions of a second. This isn't science fiction, it's quantum reality. And it's incredibly useful. Superposition is the engine behind quantum computing. Machines that don't just use bits that are on or off, but qubits, which can be on-off or both at once. This gives quantum computers the potential to process vast numbers of possibilities simultaneously, solving problems that would take classical computers millions of years. But for now, let's return to our box. When you finally open it, when you observe the system, you find the cat either alive or dead. One outcome, one reality. But until that moment, the system was a blend of all possibilities. That's the uncomfortable truth of quantum mechanics. Before the measurement, reality is fuzzy. Only afterward does it become definite. It forces us to ask, what is real? Is the cat truly both alive and dead, or is our knowledge of the cat the only thing that changes? Schrödinger himself wasn't trying to suggest that real cats live in limbo. He wanted to show that quantum theory, when taken to extremes, seems to defy common sense. But experiments have since shown that the theory holds up, even when it gets weird. So maybe the problem isn't with quantum physics. Maybe it's with our common sense. In the next chapter, we'll explore one of the most mind-bending consequences of quantum mechanics: entanglement, a phenomenon Einstein called spooky action at a distance. It's the idea that two particles once connected can influence each other instantly, no matter how far apart they are. If superposition challenged your view of reality, entanglement might just change how you think about space, time, and the universe itself. There's something in quantum physics so strange, so counterintuitive, that even Einstein, the father of relativity, the man who bent space and time, couldn't accept it. He called it spooky action at a distance. We call it entanglement. Let's start with the basics. Entanglement happens when two particles, say a pair of electrons, become deeply connected in a quantum way. Once entangled, whatever happens to one instantly affects the other, even if they're separated by vast distances. It's not a signal. It's not a message traveling between them. It's as if they're not two separate things at all, but one shared system stretched across space. Here's how it works. Imagine creating two electrons with opposite spins, one spinning up and the other down. They're produced together, like two sides of the same coin. You don't know which is which yet, but you know they're opposites. You then send one of them far away, to another lab, maybe even on the other side of the planet. Now here comes the weird part. The moment you measure one electron's spin, say it's up, the other one instantly becomes down, even if it's thousands of kilometers away. No delay, no signal traveling between them. It just happens. This isn't just theory. It's been tested over and over again. Physicists have done experiments with entangled photons and electrons, separating them by great distances and measuring their properties. Each time they've found the same result. The measurements are perfectly correlated. All when one goes up, the other goes down. Always. Instantly. Einstein hated this. He believed in local realism, the idea that objects have definite properties, and nothing can influence something else faster than the speed of light. He thought there must be hidden variables, some unknown factors that predetermined the outcomes, like a secret script both particles were following from the start. But in the 1960s, physicist John Bell came along and changed the game. He created a mathematical test, now known as Bell's inequality, that could distinguish between quantum mechanics and any theory based on hidden variables. When the experiments were run, and they've been run many times since, quantum mechanics won, every time. No hidden variables, no secret script, just entanglement. So what's really happening here? One way to think about it is this: entangled particles don't have definite properties until we measure them. Until that moment, they exist in a shared superposition, a kind of joint probability cloud. It's not that one particle knows what the other is doing, it's that the system as a whole doesn't split into two separate realities until we look. This raises a profound question: is space even what we think it is? Because if entangled particles can affect each other instantly, distance doesn't seem to matter. It suggests that information, or something, exists outside of space and time, that the deep structure of reality might be more connected than we ever imagined. Today, entanglement isn't just a curiosity, it's a tool. It's the foundation of quantum teleportation, a technique that transfers the state of one particle to another, not the particle itself, but its information. It's also the secret sauce in quantum computing, where entangled qubits allow computations that would be impossible with classical machines. And it's the backbone of quantum encryption, which promises unbreakable codes, because any attempt to intercept an entangled message immediately changes the system, revealing the intrusion. But despite all these uses, the mystery remains. Why does measurement collapse the wave function? How do entangled particles stay in sync across distance? Is there a deeper layer of reality we haven't uncovered yet? Einstein never accepted entanglement. He believed that spooky action meant the theory was incomplete. But experiment after experiment has shown quantum mechanics, strange as it is, works. It may not give us a picture of the world that makes sense in our everyday language, but it gives results that match reality better than any theory before or since. So here we are, in a universe where two particles, born together, remain connected forever, where distance may not matter the way we think, where what happens here might instantly affect what happens there. It's not just spooky, it's revolutionary. In the next chapter, we'll turn our attention to the forces that hold the quantum world together, the quantum fields that ripple beneath everything. Because if entanglement connects particles, then fields connect everything else. We'll discover how particles are really just excitations in invisible fields, and why the vacuum of space is anything but empty. Close your eyes and imagine space, not outer space with stars and galaxies, but the space between everything, the air around you, the empty void between atoms, a perfect vacuum. Now imagine that vacuum is not empty, because it isn't. Welcome to the world of quantum fields, a world where space itself is alive with invisible activity, a world where the most fundamental stuff of reality isn't particles, but fields, vibrating, shifting, ever-present fields. This is one of the deepest truths in modern physics. Particles are not tiny things. They are vibrations. They are ripples in fields that stretch across the entire universe. Let's break that down. In classical physics, a field is something that has a value at every point in space. For example, a weather map might show temperature across a country. That's a field. Or a magnet creates a magnetic field, invisible, but you can feel its effects. In quantum physics, we take this further. Every type of particle, electrons, photons, quarks, is linked to a specific quantum field. There is an electron field everywhere in the universe. When a ripple appears in that field, we observe it as an electron. No field, no particle. Same goes for light. A photon is just a bump in the electromagnetic field. Quarks, the building blocks of protons and neutrons, ripples in the quark field. There are dozens of these fields, and they all overlap, all the time. It's like the universe is a vast invisible ocean, and particles are splashes on the surface. What we call matter, atoms, you, me, everything, is just the visible tip of a much deeper, more mysterious sea. But these aren't smooth, gentle fields. They're restless. Even in total darkness, Even in a vacuum with all the air sucked out, the fields still buzz with activity. This is called quantum vacuum energy, and it's never truly zero. Even nothing is something. In fact, that restless nothingness can produce real effects. For example, two metal plates placed very close together in a vacuum will feel a slight attraction. This is called the Casimir effect, and it happens because the energy in the quantum fields between the plates is slightly less than the energy outside them. The plates are literally squeezed together by the fluctuations of empty space. Another wild result: virtual particles. These are brief flickering pairs of particles and antiparticles that pop in and out of existence too fast to be directly seen. But their effects are real. They slightly shift the energy levels of atoms. They play a role in the Hawking radiation that slowly evaporates black holes. In quantum field theory, often called QFT, this all makes sense. Fields are the main actors, particles are their side effects, and these fields can interact. One particle can create a ripple in another field, causing a reaction. That's how forces work in the quantum world. For example, the electromagnetic force is carried by the photon field. The strong nuclear force is carried by gluons, which ripple in the gluon field. Even the weak nuclear force responsible for radioactive decay is carried by its own special fields, the W and Z bosons. All of this, every force, every particle, is part of a vast interconnected tapestry of fields. The masterpiece of this idea is the Standard Model of Particle Physics, a kind of quantum field blueprint that describes almost everything we know about the particles and forces of the universe. It's been tested to insane levels of accuracy, and it keeps getting it right. But there's one piece that brought the whole picture together: the Higgs field. The Higgs field is different. It gives mass to particles. Without it, everything would just fly around at the speed of light. But thanks to the Higgs field, particles slow down, gain inertia, and matter forms. And just like every other field, the Higgs field has a particle, the Higgs boson. It was predicted for decades, and finally discovered in 2012 at the Large Hadron Collider. It was a moment of triumph, the last missing piece of the Standard Model puzzle. So when you look around and see stuff, you're really seeing vibrations in invisible fields. Fields that ripple and hum beneath your chair, through your skin, across the stars. It's as if the universe isn't made of bricks and mortar, but of music and motion, a cosmic symphony playing in the silence of space. But this beautiful picture isn't perfect. Quantum field theory works incredibly well, but only for 3 of the 4 fundamental forces. Gravity doesn't quite fit. Despite decades of effort, physicists haven't found a way to merge Einstein's curved space-time with the jittery world of quantum fields, and that's where we're heading next. In the next chapter, we'll climb higher into the search for unity. We'll explore the dream of a theory of everything, one equation to explain it all, from string theory to quantum gravity, from the tiniest vibrations to the shape of the universe itself. Because the quantum story isn't finished yet, and some of its biggest mysteries are still ahead. The deeper we dive into quantum physics, the more astonishing the picture becomes. Particles aren't tiny billiard balls, they're ripples in invisible fields. Space isn't empty, it's buzzing with quantum energy. And reality, at its most fundamental level, is built on uncertainty, probability, and strange connections that defy space and time. But there's one big problem. Our best theories, the ones that describe how the universe works, don't quite get along. On one side, we have general relativity, Einstein's masterpiece. It describes gravity, the bending of space and time, and the grand structure of the cosmos. It's smooth, elegant, and continuous, like a great curving fabric that shapes the motion of planets and galaxies. On the other side, we have quantum mechanics, jittery, probabilistic, and powerful. It rules the microworld of atoms and subatomic particles. It explains electromagnetism, the nuclear forces, and the behavior of matter at the tiniest scales. Both theories work incredibly well. They've been tested and confirmed, again and again, but they don't fit together. Try to plug quantum mechanics into general relativity, and everything breaks down. Equations explode into infinities. Space and time lose their meaning, especially in extreme places, like the center of a black hole or the very first moments of the Big Bang. The two theories clash. And that's why physicists have been chasing something more, something deeper. They call it a theory of everything, a single framework that can unite the laws of the big and the small. One theory to rule gravity, quantum fields, and all the forces of nature. It's the holy grail of modern physics. But how do you find such a theory? Let's look at a few of the leading ideas. String theory. What if particles aren't points, but tiny vibrating strings? That's the central idea of string theory. According to this bold proposal, every fundamental particle, electron, quark, photon, is actually a different vibration of a one-dimensional string, like different notes on a violin. In this framework, gravity and quantum mechanics can coexist. In fact, string theory naturally includes a quantum version of gravity, something no other theory has successfully done. But there's a catch. For the math to work, string theory requires extra dimensions, not just the 3 of space and 1 of time, but 10, or even 11. Most of these extra dimensions are thought to be curled up, tiny and hidden, impossible to see directly. It's a beautiful theory, elegant, ambitious, and for decades it looked like our best hope. But so far, string theory hasn't made predictions we can test. It offers a vast landscape of possible universes, maybe too many. Some physicists worry it might never be falsifiable. Others believe it's still the key to the ultimate theory, just waiting for the right insights. Loop quantum gravity. Another contender is loop quantum gravity. Instead of starting with particles or strings, it starts with space itself. What if space is not smooth, but made of tiny discrete loops, like a woven fabric at the Planck scale, the smallest scale in nature? In this theory, gravity arises from the twisting and interweaving of these loops. Time and space are quantized, just like energy in an atom. It's a radically different picture, but it has the same goal: to merge quantum mechanics with gravity. Loop quantum gravity is mathematically rigorous, and it avoids some of the complications of string theory, but it also lacks experimental confirmation. It describes how gravity might work at the smallest scales, but it doesn't yet unify all the other forces. Unfinished business. There are other ideas too: causal set theory, emergent gravity, asymptotic safety, and more. New proposals rise and fall. Some focus on deep mathematical beauty, others try to build from observable clues, but all face the same challenge: no direct experimental evidence. We don't yet have access to the extreme energies where quantum gravity would show itself. We can't peer inside black holes. We can't recreate the Big Bang. So for now, the theory of everything remains just out of reach. Still, the search continues, not just to complete the equations, but to understand what the universe is made of, why it works the way it does, and how everything fits together. Because here's the truth: physics isn't just about numbers, it's about the story behind reality. And the story isn't finished. We don't know the ending. We're still writing the next chapter, and maybe, just maybe, you, or someone listening to this, will help write it. In the final chapters, we'll explore how quantum theory is shaping the future, from quantum computers and teleportation, to questions about consciousness, free will, and the very nature of reality. Because quantum theory doesn't just describe the world, it challenges what it means to know anything at all. So far, we've been talking about quantum theory as something mysterious, something strange, something that governs the hidden world behind the scenes. But here's the twist: quantum physics isn't just abstract theory anymore. It's becoming technology. Right now, not in some sci-fi future, but today, we're building devices that rely on the deepest laws of quantum mechanics. We're taking the weirdness and putting it to work. Let's start with one of the most exciting frontiers: quantum computing. In a regular computer, everything is built on bits, zeros and ones. Every photo you scroll past, every text you send, every song you stream, it's just a long string of digital bits being processed at lightning speed. But in a quantum computer, the basic unit isn't a bit, it's a qubit. And qubits are different, wildly different. A qubit can be 0, or 1, or both at the same time, thanks to superposition. And when you entangle multiple qubits, you don't just get more computing power, you get a kind of exponential explosion of possibilities. A quantum computer with 100 qubits isn't just twice as powerful as one with 50, it's potentially trillions of times more powerful. That's the dream. Quantum computers could solve problems that regular computers never could, not in a billion years. like simulating molecules for new medicines, cracking complex optimization puzzles, revolutionizing artificial intelligence. But building a quantum computer is hard. Qubits are delicate. They decohere, meaning they lose their quantum magic if anything disturbs them. Heat, vibration, noise. Engineers are racing to protect them with cooling systems near absolute zero, exotic materials, and error-correcting codes. And yet, we're getting closer. Companies like IBM, Google, and startups you've never heard of are building real, working quantum processors. Not quite ready for prime time, but improving fast. Quantum communication. If quantum computing is about processing, quantum communication is about sending information and keeping it safe. Here, entanglement becomes a tool. Imagine sending a message that can't be eavesdropped on, not even by the smartest hacker or the most powerful supercomputer. That's the promise of quantum cryptography. In quantum systems, measurement changes the state. So if anyone tries to intercept a quantum message, even just a peek, they leave a trace. The message is altered. The sender and receiver know immediately. This principle powers quantum key distribution, or QKD, a way of sharing encryption keys that's fundamentally unbreakable. It's already being tested. China launched a quantum satellite called Messius to beam entangled photons between ground stations. Secure quantum communication networks are being developed in Europe, North America, and beyond. The future of the internet, it might be quantum secured. Quantum sensing quantum systems are incredibly sensitive to the tiniest disturbances, and that's not always a flaw. In fact, it's a superpower. Quantum sensors are being developed that can detect gravitational waves, magnetic fields, and time itself with extreme precision. Navigation systems that don't need GPS. Medical imaging that's safer and more detailed. Earthquake detectors that pick up signals far before current tech can. These aren't science fiction. They're prototypes, some already in use. Why it matters. Quantum technology isn't just about speed or power, it's about new capabilities, doing things that were once impossible, and it forces us to rethink what technology even is. We're not just building machines anymore, we're engineering reality itself, using the rules of the quantum world, not fighting them. It's a shift as big as the discovery of electricity, or the invention of the internet, and it's happening now. But with great power comes complexity. Quantum computers could break today's encryption. Quantum systems might open doors to forms of intelligence or simulation we've never imagined. And as with all technology, there are ethical questions, security concerns, and the risk of racing ahead without understanding the consequences. That's why it's more important than ever to understand this world, not just as scientists or engineers, but as citizens, as human beings navigating the future. Because quantum theory doesn't just describe particles and fields anymore. It's shaping the tools we use, the security we depend on, and the boundaries of what's possible. In our final chapter, we'll step back. We'll explore what all of this means, not just scientifically, but philosophically. What does quantum theory say about reality, about consciousness, about free will and the nature of truth? Because after all the particles and fields, the math and machines, the real mystery may still be us. We've journeyed through the foundations of quantum theory, particles as waves, uncertainty and entanglement, quantum fields and future technologies. But we haven't yet asked the biggest question of all. What does quantum physics say about reality itself? And what does it mean for us? Let's start with the strange fact at the heart of it all. In quantum theory, the act of observation changes the system. A particle doesn't have a definite position until it's measured. A photon doesn't decide which path to take until it hits a detector. In some interpretations, it's not just that we're observing the universe, it's that the universe behaves differently when it knows it's being observed. This leads to a deep, puzzling idea. Is the observer part of reality, or part of the mechanism that creates it? This is where physics edges into philosophy, and even into consciousness. The observer problem. In classical physics, we imagine a world out there, existing whether we look at it or not. The moon is there, whether anyone sees it. The apple falls, whether anyone's watching. But in quantum mechanics, things aren't so clear. If a particle exists in a superposition of many states, say being in multiple places at once, and we observe it, we get just one outcome, one position, one reality. The wave function collapses. But what causes that collapse? Is it the detector, the environment, the consciousness of the observer. No one knows for sure. This mystery has sparked decades of debate, and several competing interpretations of quantum mechanics try to make sense of it. Interpretations of reality. Let's explore just a few. 1. The Copenhagen interpretation. The standard view taught in most textbooks. It says that before measurement, a quantum system exists in a kind of cloud of probabilities, and when we measure, we get one outcome. The observer plays a key role, but it stays vague on how or why. 2. Many worlds interpretation. What if the wave function doesn't collapse at all? What if every possible outcome actually happens, but in different branches of the universe? In this view, when you measure a particle, the universe splits. You see one result, but another version of you sees another. Reality constantly forks into parallel worlds. It's bold, it's mind-bending, and according to many physicists, it's mathematically elegant. But if every possibility is real, what does choice mean? 3. Objective collapse theories. Maybe wave function collapse is a real physical process, like a burst of noise that kicks the system into one state. This could happen randomly, or when a system reaches a certain size. In this case, consciousness isn't needed, but the theory goes beyond standard quantum mechanics and would require new physics. 4. Quantum Bayesianism and relational interpretations. These take a radical step further. They say quantum mechanics doesn't describe objective reality at all. Instead, it's about information, what we know, and how we update that knowledge. Reality is relational. There is no view from nowhere. Every perspective is partial. Reality is in the interaction. These are deep waters. No consensus exists. Some physicists avoid the question entirely. Others believe it's the key to the next revolution in science. Quantum and consciousness. And what about us? Our minds, our experience, our sense of self. Some have suggested that consciousness is itself a quantum process, that the brain might exploit quantum effects to create awareness. This idea is controversial, speculative, and not widely accepted in neuroscience, but it won't go away. The truth is, we still don't understand what consciousness is, how matter gives rise to experience, or whether the mind is just computation or something more. Quantum physics hasn't solved that mystery, but it has made the question impossible to ignore, because in the quantum world, the line between the observer and the observed is blurry. Maybe there is no line at all. What is reality? So here we are. After all the experiments, the math, the predictions and paradoxes, quantum theory still leaves us with a mystery. Not a mystery of ignorance, but of insight. A kind of built-in uncertainty about the structure of the world. Some say that means we need a better theory. Others say that's just the way the universe is uncertain, relational, ungraspable in full. Maybe the universe isn't made of things but of processes. Not static objects, but changing relationships. Maybe reality isn't out there fixed and independent, but something more like a dance, unfolding only as it is observed, lived, experienced. Quantum physics doesn't offer easy answers, but it gives us better questions. It teaches us humility, wonder, curiosity. It reminds us that even the most ordinary things, a beam of light, a grain of sand, are full of mystery when looked at closely enough. And it invites us to imagine that the universe is stranger, deeper, and more beautiful than we ever dared to believe.